Now, the trouble is I can't show exactly what I want to show without pausing the recording. So let's see if it'll work. Yeah, it's still recording. If the projector were on, but that's another issue. What I'm about to show you is the fact that starting last Tuesday, not yesterday, but last Tuesday, something between Screencast-O-Matic and YouTube just stopped communicating afternoon. And I don't know why. They'll communicate in the morning, they won't communicate after that. On my computer, when I finish a class, I upload it, and that's done within the computer. Half of it is done, and then once it gets it processed, then it sends it to YouTube. That's the second half, which isn't happening. And this is what I'm describing now. Well, anyway, that started last Tuesday. But I found out in the morning, when I'm teaching my morning classes, the programs from the night before would upload. Okay? But then, once afternoon came, they quit uploading. So I had a bunch of afternoon classes that wouldn't load until the next morning. Until Monday. Okay? Monday, nothing uploaded. Tuesday morning, nothing uploaded. And I'll show you what I'm talking about here. Finally, this morning, it uploaded. Let me see if my pen will even indicate here. Can you see that? Yeah. It uploaded. This was Monday morning's first class. This was Monday morning's second class, but it got stuck halfway because they got out of order. This is Monday afternoon. Well, this is Monday afternoon's first class. Monday afternoon's second class, it loaded it out of order, and there's Tuesday morning class. But then once this afternoon hit, it stopped on that one. So here's this morning class. It hasn't even gotten to yet. This afternoon's early class and this afternoon's late class hasn't even gotten to because it's hung up on the 227. So what this means for you is that tonight's class will probably not be uploaded until sometime maybe Friday morning. And there's a reason for that, and I'll get to that in a minute. Okay, so what I'm going to do here, let me see if this will do anything. I'm going to show you that I'm going to retry, and it starts at 50% and then ends. So what I have to do is go back here, and this doesn't do the same thing. The other one has a cancel, so I'm not going to do that here. Let me go up here, and this is a cancel. Okay? And then I have to go back and start it over again, which I do. Which one was that? 227, I think it was. No, that wasn't that one. That was this 227. It says 125, but it's 227. I hope I'm right on that. And I'll upload that to YouTube and publish it. Okay, so make sure I got them all. There was Monday mornings, Monday early afternoon, Monday late afternoon, Tuesday morning, Wednesday morning, which it started on now, Wednesday early afternoon, Wednesday just before this class, and there's the one from before. So don't anticipate seeing it. The reason, okay, I'll tell you why it might not be until Friday morning as I get to that. Let me go ahead and shut this or minimize this so we can get started on this. Okay, we'll go from current slide. Okay, now, first, are any of you taking a first mini-term course? Do you know anyone taking a first mini-term course? Okay. If you do or did, anyone at home, please encourage them to do their student course evaluations. They didn't bother opening these up until Tuesday of last week. It's something like 9 o'clock at night. They opened it up and then sent us an email at 9:20 saying none of our students had done their course evaluations yet. They had them open at 9 something in the evening, and by 9:20 they hadn't opened, and they were telling us, you don't have any students that have done the course evaluations yet. So that's administration. Yeah. So anyway, they are open now. First mini-term ends today. Second mini-term begins tomorrow. Okay? There's implications there, but basically they'll usually keep the evaluations open at least a week or so, so they've got time to do them, but they need to do them as soon as possible. All right. Now, back about midterms. That makes midnight tonight midterm, okay? First mini-term up until then, second mini-term starts tomorrow morning, okay? Now, sometime shortly after midterm, which might be tomorrow or Friday or next week, they will open up for us to do midterm progress reports, which means we have to tell which students are making D's or F at midterm so they can try to help those students get caught up, okay? So, the bottom line to that is if you have not turned in your first or second test or have an average that's a D or an F of those first two tests, then you'll probably be getting a request from somebody. So what the point is, if you can get me one of those, if not both tests, by next Wednesday, I can keep from having to do a midterm progress report on you. Now, I'm preaching to the choir here, I think, because let me just make a quick look through. I've got one student who has not turned in either test, and I think that's all. And that student's not here. So if the student is listening at home, please get that in as soon as you can. All right, the rest of you, there were a couple of you, one or two, that had not the greatest of scores, but it sort of borderline, you know, whether you have a D or an F at midterm. No one has an F except that one student who hasn't turned in anything. One student is real close to a D. So I think I'll be okay bumping that up. So, but I don't think that student's here either. So again, I'm preaching to the choir. All right, one other issue, that is school-wide issues. This one is my own schedule. Now, most of you don't come by looking for me during the week. A couple have, and Monday, Wednesday mornings are still good. Monday afternoons are still good. Monday, Wednesday morning, 8 to 10. Monday evening, 3:45 to 6. Or Friday. No one's come by on Friday, I don't think, but that would be 8 to 12. So I don't have many office hours on Tuesday and Thursday, but tomorrow I have none of my office hours that are on the schedule, okay? Because I have a meeting in Tuscaloosa that starts at 8:10. So I will not be on the Bessemer campus at 8 o'clock because I'll be probably in Tuscaloosa or awfully close to it by 8 o'clock. So I won't be there in the morning. However, the meeting gets over with about 3:30 in Tuscaloosa if they get out on time. And so I'll be driving back, hopefully getting back to Bessemer about 4:30, somewhere around there. Then I'm going to the Bessemer campus. I'll be there the rest of the day. So if you do need to see me tomorrow, sometime after 4:30 on the Bessemer campus, 4:30 to 6, I should be there. Friday, I'll be Birmingham West campus right over there from 8 to 12. Now, I do have a doctor's appointment tomorrow, but it's not until 2. So that means if I do stay after 12, I can stay as late as 1:15, but that's the drop-dead time. I've got to leave by 1:15 to make my doctor's appointment at 2. Okay. Next week, I hope things will get back normal. Okay. I don't know of any major things that are happening next week, except we got to get fall schedule done by next week. So that's another issue. Any questions on anything? Now let's see. I did notice that I've lost my pen. There it is. I believe it's summer, right? No, yeah. Yeah, I hadn't marked you here, right? Wait, what's your name? Rachel. Okay, sorry about that. Rachel Smith, right? Smith, right? Yeah, I've got two Rachels. Want to make sure I got the right one. Rachel Smith. Okay. So now I've got 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Got it. Okay. Make sure I had everybody here who was here. All right. Any questions on anything we've done up till now? Okay. Now it seems like to me, according to my mark on the page here, we finished 2.2 but did not start 2.3. Right? Okay. So 2.3, we're chapter 12, I'm sorry, 12.3. Chapter 12 is matter, and 12.3 is properties of liquids. 12.2 was properties of solids. And some of these are similar in names, but different in application. Let's start with cohesion and adhesion. And I think we probably talked about this for liquids as well as solids back when we dealt with it in solids. So I won't belabor it too much. But cohesion, just to reinforce, I don't mean to take too much time with this, but I did want to let y'all know, in case something does happen, you'll be aware of it. I just thought I was pretty tired this term just because I'm 69 years old, and you know, I'd never been 69 before. I just figured this came with the turf. I found out yesterday at my doctor's appointment that I'm very anemic. Okay, I'm taking. I think I told y'all before that I have a mild form of leukemia, and I have to have treatments 2 or 3 times a year just to knock the counts down. Okay, it's a as the nurse said, it's not curable at this time, but it is treatable. Sort of like diabetes. You don't really cure diabetes, you treat diabetes. Well, same thing here. And the drug that they got me on now, I mean, it knocks the white counts way down. I took the last treatment in January, and my counts are still in the low normal range right now. So it knocked them below normal, which is wonderful. It's way exactly what we wanted. The downside of that is the treatment also, in addition to attacking the white blood cells where the cancer is, you might say, it also attacks other cells. If it can't find enough white cells, it starts attacking everything else. And this time it really did a number on my red blood cell count too. And before it had always got me slightly anemic, but I didn't notice any difference there. This time it really knocked it down, and that explains the tiredness I've been having. I thought it was just old age. Now, he's going to put me on B12. My wife, I think, picking it up today. He said it wasn't an iron deficiency. He didn't think because the cell sizes were good, but he thought B12 might help, but he's afraid it's something to do with the chemical, and that it may be putting a protein or something on the red blood cells that tends to start destroying them. So he's going to had me do 5 more blood tests. He had already done my blood work before I went, had me go back for 5 more, 1 draw of 5 more tubes so he could check out what's going on. And if things get a lot worse, then you may wind up with a different instructor later in the term. I'm hoping that's not going to happen. Hopefully this will work out and everything will get taken care of. But if I look really exhausted sometime, I probably am really exhausted sometime. But so far, it's been okay. But I just wanted to let you know, in case the worst happens, that we'll take care of it. We got another physics instructor. He's pretty much loaded to the gill now, but he can teach this with his hands behind his back. So he's good. All right, cohesion. What is cohesion? Now, I think we had this before. Force of attraction between like molecules. Okay, between like molecules. Now there, and by the way, here's how I remember. Cohesion, co means with. So it's between like molecules, other molecules of the same kind. Cohesion. The example they give, it causes a liquid like molasses to be sticky. It sticks to itself, but it sticks to everything else too. Okay, so to me that's not the best example, but it's the tendency of a liquid to stick to itself. Okay? Water is notoriously cohesive. I think I gave this example before when we were talking about solids, even though it was a liquid. If you've ever dived into a pool and done a belly flop, you know that doesn't feel good. Well, water's a liquid. That should separate real easily. Those water molecules stick to each other, and it takes force to break them. You can actually, if you very carefully lower a needle onto a glass of water, still water, it will float. Even though steel was certainly denser than water. It should sink, but it floats because of that cohesion of water molecules. We'll see other examples coming up later. Okay? Adhesion. Okay? That's the force of attraction between unlike molecules. Okay? It causes molasses to stick to your fingers. They use the same example. Like I said, molasses sticks to everything, so it's not very much the best. But adhesion, think of adhesive tape, right? That's tape that sticks tape to anything else. Gauze, your skin, your hair on your skin, you know, it sticks to everything. Usually, think of this adversarial. Those are unlike things, okay? So that's unlike molecules. Cohesion, like molecules. Adhesion, unlike molecules, okay? In the case of water, its adhesive forces, they say, are greater than cohesive forces. Some of the water remains on. If you put a glass of water into a sink of water, pull it out, some of the water molecules stay on the glass rather than being pulled back into the water. I'm not sure that indicates it's stronger, but it is true. Here's another example, and you can do this at home. Do it in a sink or somewhere you won't mind getting wet. Have a glass sitting there and start putting water in, okay? And keep adding water till you think it's full. You think it just can't hold any more. Try adding a little more water. And what you'll see, if you add it slowly and sort of softly enough, you'll see that you can keep adding water until the water actually mounds on top. Try it. You know, you'll see a little meniscus like this. And the reason is the water molecules are hanging on to each other, cohering to each other, trying to keep them from falling off. After some point, yeah, they will fall, okay? It will spill. That's why I said do it in a sink or somewhere you don't mind getting wet. But I do this in lab when we have physics labs, other physics labs. Anytime we're filling something with water, I say, oh, add a little more. Oh, no, it goes, well, add a little more. And people will be amazed. They say, hey, that's over the top. Yeah, add a little more, and it will finally at some point start spilling. But that's water will cohere to each other, the molecules. Okay? They also, and they say here, in the case of mercury, the opposite is true. Mercury coheres to each other, cohesive to each other, far stronger than adhesive to most other things. But that's not all things. If mercury inside a thermometer tube, and you probably, most of you have seen that, the silver liquid inside of a thermometer tube, if you look at that, the top of it, you'll see it's rounded downward. If you have alcohol in that tube, the ones that are red looking, you'll see it rounds upward. And we'll see that coming up later too. And that's because mercury coheres. It doesn't like to touch the glass or the plastic or whatever the tube's made of, whereas the alcohol likes to do it and it actually pulls up. The very example I talked about before, a needle floating on water, will be, that's because the water molecules are so cohesive. And they'll sort of form a film there, the needle will sit on top. But if you add just a little drop of liquid soap, the needle falls. And it's not because you disturb the water. You know what soap does? Does soap really, in a sense, clean something? No, a soap breaks that surface tension of water. Soap is actually called a surfactant. Surfact means surface tension, okay? It breaks that surface tension, making the water wet better, so then it'll wash your clothes or your dishes or other things. Especially if the dishes or your clothes have an oily or greasy substance on them, water won't touch that. You can wash that till the cows come home, it'll still be greasy. Add a little bit of soap, the surfactant breaks that surface tension of water and enables it to lift off the grease or the oil. Okay? So that is the next term they have here, is surface tension. So I moved right into that from cohesion and a little bit of adhesion. Surface tension. Okay? The ability of a surface of a liquid. We don't want surfaces of solids, those don't make any sense. Okay? Of a liquid to act like a thin, flexible film. Okay. Just like jumping into the swimming pool, that water acts like a boundary there that you have to break through. If you've ever noticed the high divers in the Olympics and stuff, when they're way up on those towers, they come down, they have their hands like this. They have their head tucked in, because if they, and even with that, they'll jam fingers sometimes because that water has such strong surface tension. So if you'll notice, are the Summer Olympics coming up soon? Or is that, this is even year. I think they are coming up this summer, okay? It's supposed to be in Tokyo with the virus, so we don't know if they're going to happen or not. So, but anyway, if you'll notice, those when they're diving, you'll notice the water is always being disturbed. They either have something spewing out onto the water or something. The reason is to break that surface tension. Otherwise, those divers, if that water is perfectly glass-like flat, they can jam fingers. If they land poorly, they could actually separate joints. I mean, it's a pretty mean thing. Surface tension, the ability to act like a thin, flexible film. And that's what's holding that water when you overfill the container. That surface tension is hanging on to those molecules of water just like it was a thin, flexible film. All right. Excuse me, I got to sneeze. Sorry. The next property of liquids is that of viscosity. Anyone know what viscosity is, or any context for viscosity? especially you guys, I wonder if you've ever changed the oil in your car or some other device. Those numbers at the top of the oil can, 30 weight, 10W30, 10W40, seen those? That is viscosity, okay? It's the internal friction of a fluid caused by molecular attraction. See, everything goes back to that molecular attraction. Let's go back to our, what were we talking about before? The molasses. If you've ever tried to dip into molasses or something, especially if it's cold, it's almost like a solid. Okay, you have to really spoon because that internal friction in the fluid doesn't want that spoon to dip in there. Okay, that's viscosity. Whereas alcohol, very low viscosity. There's no, I mean, it's just really easy to pour or do anything else with that. So your oils, viscosity are important there in your motor oil because you want that oil to coat those pistons and cylinders and to make sure there's no friction there. And if they're too viscous, they won't actually make the way between that, but not viscous enough, and then there's friction there. So you have to have a balance. And that's why the 10W40s and 10W30s are blended with oils of various viscosities, so you have a combination of all those. In the wintertime, you want a lower viscosity oil because the cold temperatures makes it more viscous. And in the summertime, you want a higher viscosity oil because the heat makes it less viscous. So you want to be able to coat. That's viscosity. They show the picture in the text. Oh, I wish they had these on the slides, but they don't. If you've ever seen a drop of mercury on a countertop or something, number one, you have a hazard there because mercury is a carcinogen. You don't want it around. But if you do, it almost forms a perfect little ball bearing, it looks like, except you touch it and it's a liquid. But it's trying itself not to touch that surface at all. You put a water droplet in space, it's a perfect little sphere. On the anywhere in the Earth's gravitational field, it is teardrop because the bottom is pulled down faster by gravity than the other. So those are just examples. And then the one on the oil, cold oil, very viscous, warm oil, same oil, flows freely. Okay? And basically, when you have a grease or something like that, you probably experience this. I'm thinking of lard, but no one uses lard anymore. Margarine or butter, actually, when it's cold, it's hard like a brick. You let it sit out a while, it gets less hard. You put it in a pan, and it actually turns into a liquid. So you see it's getting less and less viscous the more you heat it. And then we get to capillary action. And that's where the next slides will come from. Behavior of a liquid that causes a liquid level in a small diameter tubes to be different from, this is not a very good phrase, okay? Small diameter tubes, either to climb the tubes or to sink in the tube. Okay. And again, this comes from that surface tension and adhesion and cohesion. All of it goes back to this. And let's go to the slide and hopefully it'll make a bit more sense. So I'm going to get out of this. Have y'all got this okay for me to move on? Okay. Because I need to get to the other slide. And this isn't the best one, the one at the top. I thought this was one at the top, but we can deal with this. Okay? Now, first, they say several things here, and some of them are pertinent and some are not. But I'm going to use this other slide to begin with. If your tube is big enough, and certainly this one here is quite big, but these others are pretty good sized tubes, and you can't tell much difference in height there, and that's because a liquid seeks its own level most of the time. However, if you have a variety of tubes, especially very small diameter tubes, these are tiny little diameter tubes, but they are of different diameters. I can tell you right now, since this is the same liquid down here, the ones that are higher up in the tubes, those tubes are smaller diameter. The ones that are lower down in the tube, these are large diameters. And that's because the capillary action, the smaller the tube, the more effect that surface tension has on it. Now these are liquids that adhere more than they cohere. Because well, they do both, okay? Here's one, okay? This is water. Water adheres, and this is a very small capillary tube, okay? And in that capillary tube, because water tends to attract the sides of the tube, but the tube sides are so close because it's a very small diameter tube, then they're attracted and suck up the tube very easily. A bigger tube, they're not sucked up as far because the diameter is larger and the water can only hold up the other water a certain amount because it's the cohesion or the adhesion here that's pulling it up, and that the cohesion is pulling the middle part up. Here, the middle part is so much closer, the adhesion is even stronger. In a large tube, okay, it doesn't go up nearly as far. Okay. What notice what's happening in all these. Sometimes it's harder to tell. In every one of these, you see what they call meniscus is the surface is concave. It's down like that, okay? That's a concave meniscus, meaning the water is being pulled up the sides of the tube, and that's dragging the water in the middle through cohesion up for a little ways anyway. And you see even the water here on the outside of the tube is crawling up the tube a little bit. However, mercury doesn't do that. Mercury, because its cohesion is so incredibly strong, and it doesn't like to get on anything else, especially glass or something, it's trying to stay away from that tube as much as it can, so its meniscus is what they call convex, upward, because it's trying to get away from the tube, and the mercury molecules are getting as far away as they can. And when you stick the capillary tubes into a pool of mercury, they actually sink because, and you see they're also sinking around the edges too, on the outside, because Mercury doesn't like to touch it, so it gets as far away as possible. The smaller the tube, the more they make it sink, okay? Because that forces of adhesion, it's rejecting the adhesion and getting as far away as possible because those tubes are so close together, it gets even further away. So that's why a mercury meniscus is upward, a water alcohol meniscus caves down. Okay? But that illustrates capillary motion. Now, when do you hear capillaries talked about? Say in your biology class. So, yes, your arteries. Okay? What's happening in a capillary? These are veins. You have arteries in there probably about the same size as veins. Okay, here's veins here. Arteries in there somewhere, they're deeper. But the capillaries are where you can't even see them. They're finer than hair, probably. Tiny. And that's because of that, it's the capillary where all the action is. That's where the gases exchange, oxygen, carbon dioxide. That's where nutrients are exchanged, sugars move out, waste products move back in. That's where all the action occurs in those little tiny capillary tubes, capillaries in your veins. Now, some of you may have done this before, but you probably have seen it done. When they prick a finger to get a little bit of blood, just a little bit, especially for a diabetic kid or something like that, and then they have that tiny, tiny little capillary tube. They hold it up near that drop of blood. It just shoots up in the tube, right? That's capillary action. That's this kind of action right here happening because the blood adheres to the sides of that tube. Usually it's a plastic, I think, but it could be glass, and it just sucks it right up, and then they can take their sample with that. Okay, that's capillary action. Okay. Any questions on that? And I've already mentioned the term meniscus. Let's see if they don't have it on here. Okay. So let me, because it is a bold term, let me reference it here. Let me get my pen back. Okay. All these are menisci. Okay. Concave meniscus, convex meniscus. Okay? What a meniscus is, it's a rather weird looking word, meniscus, meniscus. The crescent-shaped surface of a liquid column in a tube. Especially a capillary tube, okay? But any tube will have a little bit of one, okay? And it can be either convex, that's like mercury, or concave. Okay, that's like water, alcohol. Those are concave. Now, I can remember the first time I ran into that combination of words, the teacher saying, you know, it's sort of like a cave. This is concave, and you're entering the mouth of a cave. Convex is going the other way. There's nothing much I can say for that. And then there's a blurb in the book on oil viscosity. Oh, wait. This is not crucial, but let me go over it since they did list these. Experimentally, scientists have found that, number one, liquids rise in capillary tubes, they tend to wet, and are depressed in capillary tubes, they tend not to wet. That's what we're talking about with water, alcohol wetting them, mercury not wanting to wet them. Number two, elevation or depression in the tube is inversely proportional to the diameter of the tube. The smaller the tube, the higher the rise or the more it falls. Okay, just like we showed here. That's what these are showing. And number 3, the elevation or depression decreases as temperature increases. As you start heating these liquids, then their surface tension, their adhesion and cohesion gets reduced, so they actually fall. Okay? Fall if they're concave, rise if they're convex. They actually decrease the amount of elevation or depression. And then there's the blurb on oil viscosity. The gal here changing the oil in her car with probably a blend. Okay. They call that W weight, and that's sort of okay. It's not really a weight issue, but it's a viscosity issue. So that was 12.3. No questions, no problems for that one. So let's move on to 12.4, which I'm going to, everybody got this one done? Go back to my other slides and go back to current slide, and let's talk about some properties of gases. They mention 2 and then one more word that's highlighted. That's bolded. First, gases. Now, let me pause this. All materials, practically every material, when you heat it, it expands. When you cool it, it contracts. Okay? That's true of solids, that's true of liquids, and it's true of gases. Solids, very, very small expansion or contraction. Incredibly small. Okay? Liquids, maybe just a little bit more, but still pretty small. Gases, big time. So that's why they didn't mention it until now. Solids and liquids do expand and contract with changes of temperature. Gases, however, do it in spades. They do it big, big time. Okay, so expansion, that's the first thing. Now, I do want to say this. I think I mentioned it before. Water is one of the most unusual, even though it's the most common substance on the surface of this planet. It is one of the most unusual substances due to its properties. And here's one of the properties that makes it so incredibly unique. Water, indeed, does contract when it cools. It contracts when it cools. It contracts when it cools until it gets down about 4 degrees Celsius. That would be close to 40 degrees Fahrenheit. No, yeah, something pretty close to that. Okay? And then once it gets past 4 degrees Celsius, it starts expanding. Just about the only substance on the planet that actually expands when it cools. What's the ramification of that? I think I've asked this before, but if not, you need to know. Addison, could I ask you what's in your cup? Lemonade. Anything in the lemonade besides lemonade? Is it really cold? What you got? You got ice in there. Okay. Is the ice at the bottom or at the top? Why is that? It's a solid, isn't it? But ice floats. Ice is solid water, yet it's lower density than liquid water. And the lemonade is mostly water. Okay? That property of water to expand in those 4 little degrees, between 4 degrees Celsius and 0 degrees Celsius, water expands, and it expands pretty big time too. Okay? Now what's going on there, and we talked about this when we talked about the phases or the states of matter. When water's a liquid phase, those molecules, like I said, hang together really tightly. But when it starts getting colder and they're moving more slowly, and then they go to get in their crystal structure, which is making ice, just before it freezes, they actually move further apart, because to get into their crystal structure, they have to move further apart. And that's what makes ice float. Okay? Now, there's some good ramifications for that and some bad ones. The good one is we have life on this planet. Wait, what does that have to do with ice expanding? Well, if you think about every lake, pond, river, anything in a very cold part of the world where it freezes, if it got denser when it got colder, then the ice would form at the bottom and work its way to the top. All life would be killed in that. All life in those rivers, ponds, streams, lakes, and whatever. And if that stuff dies, we probably are going to die, because everything on Earth is tied together. But because ice is more expansive when it freezes, it floats, and you get an air pocket between the liquid water, which is very cold liquid water, and the ice up here, and therefore animals have the opportunity to breathe. And you don't kill all the animals by freezing. Okay? They're already conditioned to handle really cold temperatures, but they can't handle solid ice. They can't be suspended in that. So, expansion is the first of, that's the negative or the positive feature of ice expanding. The negative feature of that, do y'all remember back when we had the Arctic vortex that came down from Canada and just dropped the temperatures around here into the lower teens and even the single digits? This was about 6-7 years ago. You don't remember? Oh, you weren't here then. Does anyone remember that? I especially remember it because we had pipes burst. Metal pipes break. What broke those metal pipes? Water freezing to ice. You talk about a force. If it can break a metal pipe, that's some force behind it. And you hear people talk about that. Oh, it got so cold it burst my pipes. That also happens with cars. If you don't have antifreeze in that radiator and you just have water in it and the temperature gets down below freezing for long enough, you have a cracked head. The entire head of that automobile breaks. You have to get a new engine or at least a new head. And those are expensive. You do not want that to happen. Okay? It's not a minor thing. Okay, so let's hit expansion. Okay, the property of a gas, now we're talking about gases now. Property of a gas in which the rapid movement of molecules cause the gas, I can't write, to occupy, oh goodness, this is actually talking, to occupy the volume of the container. This is not talking about change of temperature. Okay, remember back when I said if I opened the bottle of ammonia up here, and then I remembered I had to go do something? After a while, rants would be, clogging up because of that ammonia, and after a while even tea would be. It would just be permeating the entire room. That's because the gas expands to occupy the whole. Because you see, the gas molecules don't hang around together. They bounce off each other. And if they got a big container, they bounce in the whole container until everybody in the room and maybe in the building will smell that ammonia. Okay? That's what we mean by expansion. You add more heat, it expands more quickly. Okay. That's one thing. Another is diffusion. Another property of gases. The process by which molecules of a gas mix with the molecules of a solid, liquid, or another gas. Now, I think this is a fairly weak definition. That's the one the book uses here. Come on back. Okay. Now, same principle I'd said, expanding to thing. I mean, these are almost the same thing. Let me give what I consider a better definition of diffusion. Diffusion is the movement of molecules because of a concentration gradient. If you have a high concentration gradient of ammonia molecules in this bottle here, you open the top, those molecules are going to move to areas where there's a lower concentration. That's what's happening. Diffusion is the movement of molecules due to a concentration gradient, always going from high concentration to lower concentration. Okay? Now here's a dumb example I give because I like to garden, either vegetable gardening or plant, flowers, that kind of stuff too. Always I'm trying to make beds, whether it's vegetables or things, and always the Bermuda grass in my yard goes from the high concentration in the yard to the low concentration in my flower beds. Okay, it always does that. Okay, that's diffusion, going from high concentration to low concentration. You pull everything, and here they come again and again and again, going from high concentration to low concentration, following the concentration gradient. Now, notice they said that a molecule of gas can actually penetrate a solid. Okay, they actually penetrate liquids. I know you probably run into this before. I know I do have a little refrigerator in my office, and sometimes I'll have a Coke that I've opened but not drunk all of it and put it back in the fridge. Pop top, no way to seal that back, but might have an old piece of pizza also in the fridge. The next day I go to drink that Coke, it tastes like pizza, okay? If you don't have something covered, it's going to pick up odors. Those are the gases from one material diffusing into the other materials, okay? Going from high concentration to low concentration. All right. Now, and by the way, then they mentioned the heat. The heat will speed up the expansion process. It speeds up the diffusion process as well. And then the last bold thing in the properties of gases is this one. What is a fluid? What do you think of when you think of fluid? A liquid. That's what most of us think of. But what technically a fluid is a substance that takes the shape of its container. And guess what? Gases take the shape of their container too. The gas in this room is in the shape of this room, right? It doesn't bulge out. It doesn't contract away from the walls. It takes the shape of the thing. You can breathe this air wherever you are in the room. It takes the shape of the container. So a fluid is either a liquid or a gas, okay? That's the difference. So in physics, you'll hear people talk about fluid flow or fluid dynamics. That's how blood goes through your veins, your arteries, and your capillaries. That's fluid flow. Water in a pipe. It's also how air goes through a ventilation duct. That's fluid flow. The same principles that govern this govern that. Okay? That's all fluid flow. So, a fluid is either a liquid or a gas. It doesn't have to be a liquid. That's all that 2.4 is. We just finished it with 3 words. Okay? 3. definitions of words. So let's move to 12.5, which is the biggie. Okay? We talked some when we were dealing with solids of pressure or stresses. Okay? Here is the second big topic in this chapter, and this is density. Okay? 12.5. So I'm going, all right, to erase this? Okay. Density is the property of all three states of matter. I'd say all matter. There are actually two kinds. One we call mass density. Okay, now this sounds like a dumb question, but it does have meaning to it. In which system of measurements do you think mass density is used? The SI system or the U.S. customary system? SI for sure, because we don't use mass in the U.S. customary. The unit for mass there is a slug, and when's the last time you went to the grocery store and said, I want 4 slugs of potatoes? No one says that, you know. Pounds maybe, that's force, weight, but you might say 4 kilograms of potatoes, that is a mass. Okay, so mass density, and this book uses the symbol D sub m for mass density. And that's defined as the mass per unit volume. Okay, mass per unit volume. Whereas weight density, and that they use D sub W, is weight per unit volume. Okay? Now you can use weight density in SI units as well, but that would be newtons per cubic meter or something like that. But most of the time they use kilograms per cubic meter, mass volume. But in the U.S. customary, it's almost always pounds per cubic inch, pounds per cubic foot, whatever. Those are the weight densities. Okay? So the formula, dm is equal to mass per unit volume. Remember, volume is a capital V because velocity is a small v. That's what we use those for. Whereas weight, density due to weight, weight density, is force due to weight, F sub W. Remember, that's what it was. That's what we measure your weight in. Force due to weight divided by capital V volume. So those are the two formulas we use. Mass density, mass per unit volume, weight density, the force due to weight per unit volume. That's why I said you could talk about in SI units newtons per cubic meter, but most of the time they deal with mass volume, kilograms per cubic meter, or something like that. Okay? The SI units, most of the time, will be kilogram per cubic meter. Okay? That's most of the time. Not always. You can use other units. Okay? The ones we use most of the time for weight density are pounds per cubic foot. Okay? Not always. When you talk about gases, quite often you'll say pounds. Well, no, I'm sorry. Yeah, pounds per cubic feet is going to be your answer most of the time. Now, the mass density for water, okay, that is 1,000 kilograms per meter cubed. Now, that's an awfully big number, okay? And they actually put a bar over the middle zero, meaning that's the 3 significant digits. Frankly, I think it's good for about as much as you want to go. Okay? Now, just to get an idea of this, and I'm going to get far from my microphone, so it's not going to pick up well. If you think about what I said before, a meter is approximately the the height of most doorknobs. Not all, but most doorknobs. And that height is about the same as the width of that door. It's a pretty wide door. So if I got that same distance away here, it would be something about like there maybe, and you pictured a block that big that you filled with water, that's going to be huge. I can't lift it. I don't think y'all can either. That's going to weigh almost a ton. In fact, probably a little more than a ton. So I don't think they want you doing that on here. It might go through, no, I don't think it would go through the floor. But the mass density of water is 1,000 kilograms, which is 1 megagram, which is 1 metric ton per cubic meter. Okay? On the other hand, the weight density of water is 62.4 D sub W for H2O is 62.4 pounds per cubic foot. Okay, now the big difference here is your volume. A cubic meter I just described. A cubic foot is about this wide, that deep, and that deep, and that, yeah, long, wide, and tall. I mean, I could carry that. 62.5 pounds, yeah, no problem with that. A metric ton, no way, because a cubic foot is a so much smaller unit than a cubic meter. Okay, but those are the mass densities in the SI unit and weight density in the U.S. customary. For water, other substances have different densities. In fact, that's what the next table is talking about. Y'all got this already? Okay. Come on. You can do it. There we go. This is probably hard to read from where you are, but these are some of the common materials. Aluminum, a fairly light metal. They make planes from it, so it has a relatively low density, 2,700 kilograms per cubic metal. If you can think of that block that I was just talking about back there, if you had that aluminum block that big, that's even much heavier, 2.5 times, almost 3 times the density of water. Okay, but weight density 169 pounds per cubic feet. You know, a cubic foot is so much smaller. Okay, brass much denser than aluminum, 8,700. Brass is made up, I think, of copper and zinc, I think. Okay, is the other major metal that's in brass. Concrete actually is generally less dense than even aluminum, but you can't form concrete because if you think about it, this is a concrete block. What do you see here? You see pores. If you were to break that in two, you see pores in it. So it's not that dense. Okay. However, you can't make it into sheets, so they don't make airplanes out of concrete blocks, okay, because they're much too thick, okay. Copper, like I said, brass is mostly copper. Look at that, very close to the density of copper, okay. Cork, very light, that floats, so that's less than the density of water. Density 1,000 kilograms per cubic meter, 62.4. Yeah, that's it. Yeah, 62.4 pounds per cubic feet. So cork will float. Ice will float. Less than 1,000, 917, 57 as opposed to 62.4. That's why ice is floating in their lemonade. Okay. Iron, not as dense as copper, but still pretty dense, 7,800 kilograms per cubic meter, 490 pounds per cubic feet. Wood, and this is white pine, which is a fairly light wood, that would be 420. Again, less than 1,000, so it will float. 26 less than 62.4. So actually, when it floats, more of it's out of water than underwater. Okay. Now let's go to our liquids. Alcohol is less dense than water, okay, considerably. Gasoline even less. And that's why when you have a gas or an oil spill, that floats on top of water. It doesn't sink, it floats on top, okay? Mercury, though, look at mercury. A liquid, and yet it's denser than any of these metals. Even denser than lead. I misled somehow. Lead was 11,300 kilograms per cubic meter. That's more than 10 times the density of water, and so there's more than 10 times here, too, pounds per cubic feet. But mercury is even denser than lead. If you had a pool of mercury and a lead ball bearing, it would float. Not much, but it would float because it's less dense than mercury. Oil, less dense than water, so it floats. Seawater, a little more dense than water. Okay? 64 pounds per cubic foot, as opposed to 62.4. And what that means, have any of you ever been swimming in the Gulf or ocean? Do you notice anything different from a pool? It's easier to float because seawater is denser. That salt in the seawater makes it denser than regular water. Okay, even I float in seawater. Believe it or not, I'm a sinker in fresh water. I don't know how. Now, gases, you have to specify what temperature and pressure. This is what we call standard conditions. Freezing point of water, 1 atmosphere of pressure. Air, 1.29 kilograms per cubic meter. That's not much. Okay? Pounds per cubic foot, even less, 0.081. Ammonia, even less dense than that. Okay? Carbon dioxide, more dense than that. Okay? Carbon monoxide, a little less dense than that. If you're in a situation where you think there may be carbon monoxide present, good idea to get very low to the ground because it's going to be less dense, not more dense. Don't be in a situation you think there's going to be carbon monoxide. Helium, look at its density, incredibly small. And one ramification of that, the Goodyear blimp, or any blimp, is going to be filled with helium. In the old days, they filled them with hydrogen, which is even lighter. But they quit doing that. Does anyone know why? Second? Yeah, the Hindenburg. What happened to the Hindenburg? Yes, hydrogen is very explosive in the presence of oxygen. Everything's in the presence of oxygen, right? And when there was a spark, it was either a lightning strike or friction or something like that. It caught fire and was one huge fireball. And so they quit using hydrogen, started using helium, the second lightest gas. Nitrogen's almost the same as air because most of the air is nitrogen. Oxygen's a little bit more dense than air because it's a little bit heavier than nitrogen. That's the other big ingredient in air. And then propane is even a little bit denser. So these just are samples of densities of certain solids, liquids, and gases. Okay. Whoa, that was the last slide in this section, but we got more section to go. So let's go back to current slide here. All right, example 1. Find the weight density. What's the symbol for weight density? Weight density. D sub W, okay? And what's the formula for it? Uh-oh. A long time. So again, F sub W, which is weight, divided by capital V volume. Okay? Find the weight density of a block of wood, and this block of wood is 3.00 inches by 4.00 inches by 5.00 inches, a very regular block of wood, with a weight, what is the symbol for weight? F sub W. Weight is a force, so think of it as a force, and sub W for weight, okay, F sub W, with F sub W equal to 0.700 pounds. Okay? Block of wood was that. All right. How do we get weight density given this information? Multiply your length times width times height. That's good. What does that give us? Second? Volume. Okay, and what is your volume then? When you multiply those, 360.0. 3 significant digits there, 3 there, 3 there, so we put 3 here. And that would be in cubic inches, right? Because you also multiply the units. Inch by inch by inches, cubic inches. Now, the table we just had was showing weight densities in cubic feet, wasn't it? So we're going to have to do a conversion on this, okay? So this conversion, we're going from, I can't talk anymore, inches to feet, okay? I don't need my line there, but I put it. All right. Now, before you start messing with numbers, always put the units in their place. What unit's going to go where? The first line's for numbers. We're not going to mess with them yet. We'll get to those in a minute. But the second line is for the units. What unit goes where? Which on top? Feet on top and inches on the bottom. That way the inches will be able to cancel out and you're left with feet on top where it needs to be. Oh yeah, and what's the conversion between feet and inches? How many feet in an inch or how many inches in a foot? 12 inches is 1 foot. Very good. But we've got cubic inches and cubic feet. So we're going to have to cube the unit, cube the number, and unfortunately cube the number here. That's going to be a pretty big number, 12 cubed. What you're going to do is take this 60 and divide it by that 12 cubed. It's going to be a pretty small number. 0. What? Anybody? $60 divided by 12 cubed. Now, if you don't know how to do 12 cubed on your calculator, you can do in your denominator, open parentheses, 12 by 12 by 12, close parentheses. That gives you the same thing. What you get? Say again. 3, 4? Is that what you said? I can't hear well. Okay. 3, 4 feet. Okay, we probably need one more digit. You have another digit? Huh? 7. And what's the digit after that? 2. Okay, we'll drop the 2. That gives us 3 significant digits. So that's going to be our volume in cubic feet. So we'll take our weight, which is 0.700 pounds, and divide it by 0.0347 cubic feet, and what do you get your answer there to be? I'm going to guess something about 20 1 or 20.1. So I get 20 point what? 16. Okay, that's 2 digits there. The 1 would be a third digit, but 6 is greater than 5, so we'll round that 1 to a 2. 20.2 pounds, units are your friends here, per cubic foot. Okay, now let's look over here at your table and see what wood was. White pine was 26 pounds per cubic feet. This must be a pretty light wood to be that much less than white pine. Okay, does that make sense? The book did it a slightly different way. Either way will get there, however you want to do it. The important thing here is that when you do have an intermediate step like we did here, multiplying first and then having to do a unit conversion, always make sure you have at least enough significant digits. In fact, what I would have done, I think, is whatever those digits here turned out to be, as many as they were, I'd have used all those to divide into the 0.7 and then rounded to 3, and that way you don't propagate a round-off error. But what we did was perfectly fine. All right, so that's example 1. Ready for example 2? All right, to erase? Okay. Let's wipe out that and go to example 2. Find the mass density this time. What's the symbol for mass density? D sub m. And what's the formula for it? M over capital V, mass per unit volume. Of a ball bearing with a mass, there's our mass, M is equal to 22.0 grams. And a radius, it's a ball bearing, so its radius is 0.875 centimeters. They are really socking it to us with the units on these, aren't they? First, what was our normal, our SI unit for mass? It wasn't gram. It was, remember that table we had? Remember the door back there? Talking about how big that kilogram, exactly. So I need to get this mass in grams to some mass in kilograms. And again, what do I put the units in their place in the second blank? What unit goes where? Kilograms on top, grams on the bottom, and then you match the numbers, how many grams per kilogram or how many kilograms per gram. Anyone know? Please say yes. Kilo means, okay, you know about what a kilometer is? It's a little less than a mile, but you know what a meter is? How many meters does it take to make that kilometer? It's a power of 10, 3 powers of 10. It's a 1 with 3 zeros. 1,000. Okay, good, way to go. Okay, so 1,000 grams is 1 kilogram. Kilo means 1,000. 1,000 grams is 1 kilogram. So what you mean here, you move this decimal 3 places to the left. So this is 0.0220 kilograms. Now you might ask why you need all those zeros in there. This one really isn't doing anything for you, just pointing out where the decimal place is. But this one's not significant. Anything before the number is usually not significant, but you have to put this one in because that was significant. So it's 0.0220 kilograms. All right. Now, the second thing they did here was give us a radius. We don't need a radius. What do we need? A volume. And what's the volume of a sphere, which is a ball bearing? Does anyone know the formula for the volume of a sphere, given the radius? Okay. Usually these things are given, aha, here we go. Back inside cover of your book. If you got a book, anybody? And on the very bottom, geometric solids, there's a sphere. And it gives your radius there. It gives it in terms of, it gives the volume in terms of radii and in terms of diameter. We have radii, a radius. So what is that formula? V is equal to what? 4/3 pi r cubed. Perfect. Now, time out. I have a question for you. Ultimately, what are we going to want the units of our volume to be? Centimeters like they gave us, or something else? They usually want them in cubic meters. Remember the door back there? Cubic meters. So, you have a choice. You can first convert the centimeters to meters and then do your cubing, or you can calculate the volume using centimeters and then convert to cubic meters. And frankly, both of them are pretty rotten, but I think it's probably just about as easy to do centimeters to meters to begin with. You want to do it? It's going to give you a weird number, I admit that. A really weird number, but it will work. So we're going to have to multiply this by blank blank equal blank meters. What goes where? Anybody? Meters on top, centimeters on the bottom. How many centimeters in a meter, or how many meters in a centimeter? Anyone know? I have to pull out my pennies again. I hope I have some. Yes, there's 100 centimeters in a meter. Cents, 100 cent dollars in a dollar. 100. A cent is a centidollar. So this is 100 centimeters, makes 1 meter. Okay? Centimeters will cancel out, and this moves the decimal 2 more places to the left. 0, 0. So this is 0.00875 meters. And then, if that wasn't bad enough, we're going to cube it. Okay? So this will be 4 divided by 3 times pi. Now, most of your calculators probably have a pi key on them. If not, you can use 3.1416 if you wanted to. Times 0.00875 meters cubed. That's going to be a pretty small number. Very small number. What do you get? I'll just tell you right now, the 4/3 pi is going to come up just a little more than 4. The 0.00, I'm going to round that to 9, will come out, it's a small number. Something maybe about 0.00007, something like that. I don't know. And then multiply that by 4. What do you get if you do that calculation? It's going to be a pretty small number. lots of zeros in front. Or you're going to have it in scientific notation, which would be fine too. What do you get? Anybody? Y'all know how to cube on your calculator? Nothing else, you can put 0.00875 times 0.00875 times 0.00875. That'll do it, but it's much easier to do 0.00875 and then use the caret error or the X to the Y error, or key. There is a key out there that'll cube it. Some of you may actually have a cubing key on your calculator. If you do, just hit that one and you're fine. So anyone got an answer yet? A little slower? Seven? Okay, I'll need at least two more. Huh? Oh, that's just, yeah, okay, that's about what I thought. But you need a couple more digits. Okay, wait. That's not a 7 then? Okay. Okay. And what would be 6? 6? 9? 9. Okay, stop right there. We'll go 3 digits. 1, 2, 3. Look to the right. That 9 is greater than 5, so that'll up this by 1, which makes that a 0, but that's a significant 0. And then this will be a 7. So let's call it 0.000000670. Okay. Now multiply that by 4/3 pi. So that's just this part. So it's about times 4. I would guess that's going to be 5 zeros and something like a 2 or 3. Second. 1, 2, 3, 4, 5 zeros and what? 3, 6? Oh, 2, 6. Okay, I don't hear well. Okay, 2, 6. My wife says it's selective, but it's not, you know. Okay. 2, 6 what? 7 what? 9. Okay, again, the 9 will bump that up to an 8. So we'll call it 0.0000268. All right, so now we got our numbers we need. Let's plug them in now. Your mass is 0.022. You don't have to put that other 0 if you're using a calculator. I'll put it down. That's kilograms per unit volume, which is 0.0000268 meter cubed. This is a steel ball bearing. I'm guessing that's going to be on the neighborhood of something like 9,000 or so. I'm just guessing. Let's see. If I move this 6 places that way, it'll be 6 this way. About 9,000 or so. I don't know, I'm guessing. What you get? 0.0220 divided by 0.0000268. Anyone do it? 8,000. Okay, what is it? 200. 8. And 8. 0.8. I can't write. Okay, and that would be kilograms per cubic meter, right? Now that's pretty ugly writing, but we only need 3 digits, so we count 1, 2, 3, on that 0, look to the right, that's an 8. That'll bump it up by 1. That'll be 8210 kilogram per cubic meter. Okay. Let's see how the book did. Whoa! They got something far different. I mean, not too far, but a lot good. 7,830. I don't know if they did it right or wrong. They don't have, oh, there's iron. Yeah, they probably are closer than we are. We must have made an error somewhere, and I don't have time to go back and check because I don't have a calculator. Did anyone get a number different, or were y'all using the same number? I guarantee you the 0 point, our zeros are about right. The 0.0220, yeah. It's what? Yeah. Which one? Okay. What is it then? Yeah. What is it? Okay. After the 5 zeros, what's the next digit? 2806. Okay, we'll round that to 281. Okay, so we'll put 281 in here. That probably will do it for us. And that changes us to okay. What was it again? 29. So that will round it to 7830. Okay. And that's what they got. Good for them. Okay. Be careful with your punching. Okay. All right. Let's move on to example 3. My board is almost gone to sleep on me here. All right, to clear this. All right, let's try it again. Clear this? Yes. Okay. Find the weight density of a gallon of water weighing 64. So we've got 1 gallon of water weighing 8.34 pounds. Okay, and we're looking for the weight density. What's the symbol for weight density? D sub W. What's the formula for it? F sub W over V. Okay. Now, gallon isn't a standard unit of volume. It certainly is a volume, but it's not standard. Now I'm going to show you something now you may have already discovered, but in case you haven't, it's a good time to discover it now. Go to the back of the book and go to somewhere around page 686. There's a couple before this, but this is your Appendix C, which is your tables. They don't have any chairs or other things, just tables, okay? And these are some conversions. Table 1 is U.S. weights and measure. That goes through from units, length, and volume, and weight. It's just the standard ones, okay? If you ever need them, there they are, okay? Conversion table for lengths. Now this is going from centimeters to meters, kilometers, inches, feet, and miles. All of those. You got those 6 across the top, the 6 down the side. Okay? conversion table for area, from metric to staying within metric and within U.S. customary. And remember we did before how many cubic feet were a cubic inch? Oh, no, I mean square. No, we didn't do it. Sorry, this is area. And then they have a table at the bottom that takes you square feet, square meters, square centimeters. We could have used that one before, remember? Square feet and square inches, and they have those down the side. Then you have a conversion table for volume. That's the one we're looking for. This is on page 687. And they have the metric conversions, the U.S. conversions. But down near the bottom of that table, it says 1 U.S. fluid gallon, that's what we have here, is 4 U.S. fluid quarts. We knew that, but we don't care right now. Which is 8 U.S. pints. We know that, but we don't care right now. Which is 128 U.S. fluid ounces. Fine, but we don't care anymore. What we're looking for is how many cubic feet it is. And there's our conversion. So, the first thing we've got to do, we've got the force due to weight in pounds. That's 8.34 pounds. That's fine. But the 1 gallon we need to convert. So 1 gallon, multiply that by blank blank, equal blank, and we're trying to get to, what's our unit for volume in the U.S. customary? Cubic feet. Okay? We're trying to get to cubic feet. That's just 1 foot, not a cubic foot. All right. So what unit is going to go where? Don't mess with the numbers yet. Match the units. What unit is going to go where? Cubic feet on top this time. Gallons on the bottom. And then we go to this table right here that I found for you. Back on page 687. I keep a piece of paper there so I can find it easily. And you see that 1 U.S. fluid gallon is 0.134 cubic feet. You see that? At the end of the thing there. 0.134 cubic feet. 1 U.S. I don't need a conversion here. I can just write that down. 0.134 cubic feet. That's right there. So we didn't even need our conversion factor. It gave it to us completely. So that's what we put in our volume here, 0.134 cubic feet. Now pull out your handy dandy calculators and see what you get. I'm guessing about 60 something, because that's what it better be. What do you find it to be? 63.33? 2.23? Huh? 8. Okay? And that would be pounds per cubic foot. Okay? We don't need that many digits, so we count 1, 2, 3. On top of that 2, look to the right. That's less than 5, so we'll just throw those away and say 62.2 pounds per cubic feet. Well, we know it should be 62.4. Okay? They used 2 conversions, which the more conversions you make, the more chance you have for error, and they came out with a better answer. I can't tell you why. I think they may have done some rounding wrong in the back of the book, but guess what? If you're within 2/10, you're going to get credit for it. So don't sweat not having exact. Okay? So that was example 3. Let's move on to example 4. See if we can squeeze example 4 in. Find the weight density. What's the symbol for that? D sub W. What's the formula for it? F sub W divided by capital V. Okay. Of a can of oil, so you got 1 quart of oil. Okay, weighing, so F sub W for that oil is 1.90 pounds. Okay. Uh-oh. We got the weight right. That's in pounds, 1.90 pounds. But the volume we've got in quarts. So go back to our table and see if we can figure out what a quart is. Okay? And we want it in what units? Cubic feet. I hate to use the same one because it's the one that gave us a slightly wrong answer before, but we'll do it. I see quarts to liters. That doesn't do us any good, but I think what we need is, let's do it, times blank blank equal blank cubic feet. Okay? Now, what they have in the table, they have 4, okay, wait, what unit goes where? Cubic feet on top and quarts in the bottom, right? Now, in the table here, we have 4 quarts. So let's put 4 quarts down here, and that is 0.134 cubic feet. 0.134 cubic feet. You see that's in the table there. 4 quarts equal 0.134 cubic feet. That'll work just as well as anything. So just take your 0.134, divide it by 4. What do you get? 0. What? 0. 33. One more digit. 5. What's the next digit? That's it? Exactly. Excellent. Okay, so what we'll do, that's our volume, 0.0335 cubic feet. Okay, see what that gives us. .9 divided by 0.0335. Anybody? Okay, 56.71. Okay, we'll just do the 7. Look to the right one. We'll drop it. And that would be pounds per cubic foot. Okay. Now what I'm going to do here is go back to my table that we were looking at before when we were looking at densities of oil. They had about 54.2, so this must be a little bit heavier oil, and the book has 56.9. So again, we're off by 0.2. I don't know where that's coming from. Evidently that conversion is problematic, but that's close enough. Close enough for government work. All right, good deal. Okay, I think we can squeeze one more in, can't we? Yes. Okay. Let's see if we can. This will be a quantity of gasoline. Whoa, we don't know that. It weighs, so F sub W is going to be 5.50 pounds. That's the weight. With a weight density, D sub W of 42.0 pounds per cubic feet. 42.0 pounds per cubic feet. Okay? Find the volume. So we're looking for V. That's what we're looking for. How are we going to make that work? What formula relates weight, weight density, and volume? Been using it all night. What is it? D sub W is equal to F sub W divided by V. We want V by itself, so let's multiply both sides of the equation by V. That gets rid of it on this side. and then divide both sides of the equation by d sub w, and that gets rid of it on this side. So what we have is v is equal to f sub w divided by d sub w. That looks like it should work. Let's see if it will. F sub w is 5.50 pounds. D sub w is 42.0 pounds per cubic foot. Okay? Well, looking at these, the pounds are going to go out. They'll divide away. And the unit is left with 1 over cubic feet, which is cubic feet. So do the math part, 5.5 divided by 42. A little louder. 1309. So let's round that to a 1. And that would be cubic feet. Now, I don't know if they leave it in that or not. Oh, yes, they do. 0.131 cubic feet. They did it right. Good for them. All right, I gather by all the zipping I hear that it must be close to time. So let me erase what we've got here. And we'll be starting next time with example. Well, we'll start with the top of page 333. Okay? Now, before you go anywhere, hang on. Let's just see how much we got to go. We've only got a couple of examples left. Do you think you want to have, just for fun, the test so you can at least start working on that? That gives you an extra week to work on, if I can find where those are. I put them in here. Ah! Nope, that's the wrong one. That's the wrong. Oh, no, that's the right one. That's it. Okay. So here is the test 3, chapter 12 test. One for you. Now don't go anywhere yet, because there are a couple of corrections I've made on this. I want to make sure you can follow my corrections. Take one and test one. Does anyone know anyone else that might want you to bring them one? Okay. All right. Now, you'll notice here I did put in a couple of zeros because I can't believe anyone would be this sloppy about it. And number 3, the vertical steel columns of an office building each support a weight of 50,00 pounds. That doesn't even make sense. That should be 50,000 pounds. That other little mark there is an extra 0. Okay? And then the B part of the question, what would the compression be if the weight were 60,00? That doesn't make any sense. That should be 60,000 pounds. And I worked them out to make sure the answers were correct for these numbers, and they are. So that extra 0, I mean, that doesn't even make sense. 50,00, that's 60,00. There should be 3 zeros following the comma. Okay? Good deal. Any questions? Okay, have a good weekend, a good week, and we'll see you next Wednesday. All right. The what?
Can I take a picture of the conversions in the back of your book?
Oh, sure. Okay. Let me. Oh, good. Thank you. Okay. I don't know how many pages of this you'll need, but you can take as many pictures as you want. Okay. I'll let you set it up, get the light you need. Okay. Let me pause a moment here and put these things in the right places. And I try to keep my papers in order, otherwise I can't find a thing. Now, this is the one you turned in last time, right?
Yes, sir.
Okay. almost wish they hadn't told me what they told me, because now I can just feel so tired and know, oh, is that anemia? Where it may not be. It may be I'm just tired. You know.
You need to go home and get you some rest.
Yeah.
Do you want this open or shut?
You can close it. Just make sure that page is still back. Yeah.
Yeah,
Okay.
it's there.
All right. Just set it down. I'll get it.
Thank you.
All right. I went right past you, I think.
Y'all be careful going home.
You too.
Thank you. Oh, there you are. Okay. Yeah. That's you, right?
So, if we add both the grade from last time and this time, divided by 2,
Yeah.
then it'll show you
That's
the
your average, right?
Okay.
Yeah. Good deal.
Okay, thank you.
Uh-huh.